Yeah.
Great. All right, I'll fire away. So yeah, I want to take us on a little journey this afternoon, and end up talking about tipping positive change to avoid climate tipping points. And the arc of the talk is going to go through some work we also did on the human climate niche and published recently. But I thought I'd start with the plot here of atmospheric carbon dioxide and temperatures in Antarctica from one of the Antarctic ice core records over the last 650,000 years, because it nicely illustrates the complex systems dynamics of the Earth as a system before humans started perturbing it. We still don't fully understand the origin of this incredible sawtooth oscillation of the climate on a 100,000 year timescale. But we can see that CO2 and temperature are pretty strongly correlated on those timescales. And it's always sobering for me just to plot where we are in terms of carbon dioxide concentration, now a little bit higher than that at about 410 parts per million, and where we're heading in the rest of my lifetime on the current trends of change. And then you see it in that context, it's kind of hard not to accept that there'll be some profound changes to the Earth and to the climate as we recognize it if we carry on going up there. So I will talk about a little summary of where the current state of knowledge is on climate tipping points. But I also want to talk a bit about the fairly unprecedented temperatures that quite a lot of humans will be experiencing on the surface of this planet if, for example, we head towards around 3 degrees of global warming, which is kind of where all our collective commitments to the Paris Agreement on climate change are due to be taking us. So the journey of the talk is a kind of quick review and latest on knowledge about climate tipping points, and then continuing on the theme of the horse people of the apocalypse in that lovely woodcut there. I'll talk about this new work on the human climate niche, but then I'll try to flip it round and talk about something more positive, which is how complex systems thinking and our understanding of tipping points could be our salvation, and probably needs to be our salvation if we're going to tip the kind of rates of transformative change that we need to avoid the worst in terms of these climate tipping points or possible threats to large-scale movement of people. So let me start with just a little movie of a system that starts with 2 stable states. It can only be in one of them, but eventually, under some forcing here that's destabilizing the state that it started in, the ball that represents where the system is going to be tipped into a different state. And that was the canonical toy example of a tipping point. It's what the mathematically inclined amongst us will call a fold bifurcation or a saddle node bifurcation in a one-dimensional system. But I guess the point is we understand lots about complex systems. You're a complex systems research centre. We know now that lots of different types of complex system can, under particular conditions, exhibit tipping points of this kind, and sometimes they exhibit them of other kinds that we can come back to in the discussion. I recently tried my own summary here on axes of time scale and space scale. I tried to summarize kind of well-established or identified tipping points, or sometimes called regime shifts, in different ecological systems in blue and green, and the land-water interface in sort of murky brown there, different climate Earth system tipping points in yellow, but also social system tipping points broadly construed in red. Most of them on this map probably negative ones, but we're going to come to some positive ones later on. So yeah, complex systems, they often have nonlinear dynamics. Sometimes under particular conditions, they can exhibit these tipping point dynamics where a small perturbation can qualitatively change the future state of the system, and the resulting transition can be abrupt and or irreversible, or difficult to reverse, to put it specifically. But to move on to the climate tipping points, I won't try to run through all the work we've done on this, but in case some of the audience aren't familiar with it, the first thing you need to know is that the Earth's climate has done many abrupt changes in its relatively recent past. Most iconically, these 20 or so abrupt warming events during the last ice age, and at the end of the last ice age, which are known as the Dansgaard-Oeschger events. And they involve something like 8 to 10 degrees of warming as recorded in Greenland, and in the cases where you can resolve it, that can happen in less than a decade. So that's a pretty unprecedentedly abrupt climate change with repercussions around the planet, particularly in the North Atlantic domain. We zoom into the last 15 or so thousand years, including the end of the last ice age. And I suppose as climate and Earth system scientists, we tend to comfort ourselves with the thought that the last 10,000 years of the Holocene, in which all our agricultural-based civilizations have developed, are were relatively stable compared to the tumultuous oscillations within the last ice age. But there were also some fairly significant abrupt shifts, for example, in the hydrological cycle in the tropics at various times throughout the Holocene. And as we saw at the start, we're now pushing ourselves way off the scale in terms of these graphs with our anthropogenic forcing of the climate system. And it was more than 10 years ago that was motivating myself, John Schonhuber, various colleagues, many of them at PIC in Germany, in Potsdam, to try and put what we could then identify as systems within subsystems of the climate that could pass the tipping point. We tried to put them on one map, essentially. So this is one version of that original map, and it included something that had already happened, which is the Antarctic ozone hole, which of course is kind of non-linear chemical thing involving halocarbon reactions on the surfaces of polar stratospheric clouds, but it's certainly linked to climate dynamics, if not a wholly climate phenomenon. And pretty much everything else on the map was about things that we identified and called climate tipping elements, that we had reason to think they could exhibit a tipping point under anthropogenic climate change this century. And the question marks against some of the things were meant to indicate at the time less confidence in our assessment. But we came to this assessment from basically three sources of knowledge. Was there an underlying understanding of the mathematics and the physics and the chemistry and biology of these systems to think that there was a tipping point, by which I mean there was evidence for a strongly self-amplifying positive feedback process within the dynamics of each of these subsystems that could propel an abrupt change. That's one source of evidence that would put something on the map. Another source of evidence would be, could we see from Earth's history any signs that these subsystems had undergone an abrupt shift in the past? And then the third source of evidence was, with the models we had at the time, did we have any showing future projections where one of these subsystems or several of them underwent abrupt shifts? And those were basically the criteria that put things on the map at the time. Whenever you're considering risks, especially non-linear risks, you've got to think about two dimensions of risk. Risk in simple terms is it's the likelihood of something happening times by its consequences or impacts, in negative impacts in this case. And this was a little bit later, but still nearly 10 years ago, that I started trying to sketch out how I placed some of my tipping elements on this kind of risk matrix. And even then it was clear to me that, right, we definitely would like to have better information on the likelihood of these events, but and I'm afraid still are, really lacking good scientific information on the impacts of passing pretty much any of these climate tipping points. The one that on the impact axis that the most work has been done on is the canonical example of a collapse of the Atlantic overturning circulation. And recently, we've started to do a bit of work on the impacts of that tipping point at a rather parochial Great Britain scale, partly because we had the tools to do this, but we looked at the impacts of a collapse of the Atlantic overturning circulation and associated redirection of the Gulf Stream, which will loop its way backwards south past Spain in this scenario. How would that impact, let's say, land use in the UK? We chose to focus on that because we have a well-grounded model of land use decisions based, a data-based, empirically grounded model, if you like, where in the maps on the right you've got arable farming in brown, which is what farmers will do in the UK if they can, because it's more profitable than grassland farming in green. But in many climate situations and soil situations and so on, you can't successfully arable farm in Great Britain. And under an AMOC collapse scenario, as we call it, the simple message is, well, it's competing with global warming and having a local cooling effect, and overall you get at least a temperature cooling when this happens. But the crucial thing that happens is actually the Great Britain and much of Western Europe gets a lot drier based on at least the Hadley Centre's state-of-the-art climate model, and that's why the simple outcome is this AMOC collapse would stop pretty much all arable farming potential in the UK. That's probably would be the least of our worries if it happens. We looked at whether you could mitigate that by irrigating the land, but then we did some calculations of what that would cost and whether the water would be available to do that from the winter for the summer irrigation, and we found out that it wouldn't be, and that you'd have to build great big pipelines from the places where it was still raining in Britain, up in the mountains on the west side, the northwest of England and Scotland, right down to the southeast. So hopefully that gives some flavour of the sort of, even at a parochial British scale, of the profound changes we'd expect to see for this particular tipping point. Most of the work, as I said, on climate tipping points by scientists has been orientated around trying to assess their likelihood, not their impacts. Actually, we need both sources of information, but on the likelihood front, we, at least 10 years ago, didn't trust our models enough to only use those to assess likelihood. So there was this iconic expert elicitation done by Elmar Kriegler and others, and that came back with a simple message from the experts that these postulated tipping points, of which 5 were examined, not what many people assume high impact but very low probability events. Instead, especially under kind of business as usual warming trajectories, they should be seen as becoming high impact, high probability events. But it's taken a long time for that to sink into the economic analysis of climate change, as I'll show in a minute. In the meantime, this is one of my favourite studies that Steven Dreyfus and Sebastian Battiani and others published. They chose to look in the last generation of Intergovernmental Panel on Climate Change climate models, the CMET5 models, and they just ran an algorithm to search for abrupt shifts at a sort of local or regional scale within the climate model projections. And they found this extraordinary result that the models have a whole load of abrupt shifts clustered at about 1.5 to 2 degrees of warming above pre-industrial. It then appears to drop off at higher levels of warming, but caution is required there because there are many fewer scenarios going up to the high levels of warming. So if you correct for that, there's another peak of tipping points, if you like, up at higher levels of warming. Nevertheless, this peak at low levels of warming was a sobering one, and you might dismiss it and say, well, maybe we tuned our models to be stable at plus or minus 1 degrees of the Holocene baseline, but we never bothered to look above 1 degree and find that there are a load of instabilities there. Maybe we can come back to that in the discussion. But as we'll see in a minute, evidence from the real planet as to what's going on at now a little bit over 1 degree of warming would rather suggest that there are some instabilities in the climate system. And indeed, it's hard to rule out that we haven't already passed one or two tipping points. And that's quite a change in assessment, as this figure tries to summarise. What I've done here is I've put together the IPCC's own assessment of where are tipping point risks in terms of temperature warming above pre-industrial levels over time, where 2019 here actually refers to the two special reports on 1.5 degrees of warming, which was in 2018, and the 2019 report on the oceans and cryosphere. But the simple message, as these risk assessments have been renewed over time by the IPCC, is that the risk assessment has been going up radically. And instead of thinking that tipping points were 20 years ago, apparently the assessment was that, tipping points might be 4 or 5 degrees of warming away. Now there's a recognition, even by IPCC, that there's a real risk of tipping points already at the present level of warming, and certainly before you get to 2 degrees of warming. So that should be a big wake-up call, not just to scientists, but to society, because, as we'll see, we should be wanting to avoid these eventualities if we can. Just to say, one reason why this assessment has got more stark is, I think, because of the evidence coming from the real climate system. So this map is just my crude attempt to summarise some of the things that have been learned in the last decade, or messages or evidence-based assessments that have certainly been reinforced by what's come in the last decade. And in particular, we can't rule out, or at least my glaciologist expert colleagues convinced me we can't rule out, that part of the West Antarctic ice sheet is already past a tipping point and in an irreversible retreat. And the same thing is true for a part of the East Antarctic ice sheet, the Wilkes Basin. In each case, draining, if the whole West Antarctic ice sheet goes, an equivalent of about 3.5 meters of sea level rise, and in the Wilkes Basin, 3 to 4 meters of sea level rise. And then up in Greenland, still we can't rule out that the accelerating shrink of the ice sheet there couldn't be the beginning of the end, where if it shrinks eventually entirely, there's another 7 meters of sea level rise locked up in Greenland. The only saving grace is that that sum total of more than 10 meters to sea level rise at the moment is, if it is unfolding, it's unfolding slowly, and it'll take over 1,000 years to realise that. But the more we warm those ice sheets, the faster they go. There's a whole lot else on the map here. Maybe we can come back to it in the discussion, but it should just give a sign of that there are, from various quarters of our Earth system, signals of accelerating change in systems that some of us had already identified as potentially having these strong non-linearities in them. I also tried to summarise and link some of that information to what we already know about causal interactions between parts of the Earth system. And the concern here would have to be where you have a situation where change in one part of the Earth system that might be nonlinear tends to accelerate change in another part of the Earth system, which might also be nonlinear. And we do see connections of that kind, unfortunately, starting to show up. We can discuss how strong those connections are, but the loss of Arctic summer sea ice cover is adding to the extraordinary warming that's been happening on the Greenland ice sheet, and the meltwater from Greenland is one contributor to the observed weakening of the Atlantic overturning circulation. And we certainly know things about the relationship between weakening the Atlantic overturning circulation and disrupting monsoons in West Africa, India, and northern South America, the Amazon region. And also, if we weaken the overturning circulation, we're reducing the transport of heat from the southern hemisphere to the northern hemisphere. So we're leaving heat behind in the southern hemisphere, heat in the ocean that can be a contributor to melt of the marine grounded West and East Antarctic ice sheets. So all in all, there are, of course, couplings in the complex climate system. again, I encourage others to work on this, because this is what the expert elicitation 10 or so years ago said about those possible couplings. We could probably improve this map or elaborate it a bit now, but still there are relatively few carefully done complex Earth system model studies to really unpick these couplings, and we really ought to know more about them to understand the risks we're dealing with. Whether we're heading for a possible global tipping point would be more controversial, but unless we can 100% confidently completely rule it out, then we really ought to spend some time trying to assess whether that's a possibility, and if so, how likely or unlikely. But I'll change tack for a minute and just summarise, what does this climate tipping point risk information mean for what we should be doing about climate change? Because basically, unfortunately, economics has been dictating our responses to the climate problem, and a particular mode of analysis, economic cost-benefit analysis, which I personally think is the wrong tool for this nature of problem, and we can discuss that later. But it's been the dominant tool for this assessment, and the typical assumption is the warmer it gets, the bigger the climate damage is, and that's probably a nonlinear function. It's often assumed to be quadratic. The lower we want to hold the temperature, the more it's going to cost us to hold the temperature down. That assumption can certainly be challenged, as we'll see. And somewhere in the middle, there's supposed to be some optimum. And economists have been building models where they assume everything is deterministic. We know the shape of these curves, and therefore we can invert the matrix and solve for the optimum solution. And Bill Nordhaus got a Nobel Prize for doing that a couple of years ago, and he's been arguing for decades that the optimum is about 3 degrees of global warming. I'm going to argue that that's definitely shouldn't be the optimum. We shouldn't be aiming there. And we did a little bit of work to see how including uncertain tipping points, stochastically uncertain tipping points, into this analysis that Nordhaus does would change the outcome. So basically, his model, if you don't know it, has the acronym DICE. And we did a simple thing where we added tipping points, the possibility of climate tipping points, to DICE. And we made them a stochastic dynamic possibility, by which I mean a tipping event would be like a dice rolling event, but where the dice get loaded as the temperature goes up, and it becomes more likely to roll a given tipping point at a given time step the warmer it gets. But that's a different mathematical representation, a stochastic dynamic representation, to the original model, which is purely deterministic. So we had to do some magic in how we solve the model and switch how we solve the model to solve the stochastically uncertain problem 10,000 times under uncertainty, blah, blah, blah. Basically, what we're going to have a look at is what does that do to the outcome of the model. And the outcome of these models should be understood as you could argue it's a bit like a policy suggestion, because these models include this idea of an omniscient social planner, some godlike figure who gets to choose how much to mitigate climate change, or how much consumption levels should be in the economy based on the information they have. So if you want to put tipping points into a model like this, you've got to specify some things. You need to specify that dice rolling hazard rate and how it gets weighted as the temperature goes up. And we took that from expert elicitation that I showed you. We need to say something from what we know as scientists about how long it takes to tip different systems. That's in the middle column. And we need to make a heroic guess at what the damages of any given tipping point would be to what's called the utility function in an economic model, or in simple language, the way they often conceive it, world GDP. And Nordhaus himself thinks that a collapse of the Atlantic overturning circulation would cause a 25% irreversible loss of global GDP. So I'm just going to argue that I'm going on the conservative side when I pick numbers in a range of about 10%. And 10%, incidentally, was the hit on global GDP from the recession about just over 10 years ago. We all look forward to finding out what the hit of the current crisis is, but it's probably comparable in magnitude again. So what happens when you put tipping points that cause a 10%-ish irreversible impact on GDP to occur if they happen into the model? Well, you go from the green curve to the black curve. So here the green curve is Nordhaus's original results, including a roughly 3-degree warmer world. It's actually a bottom left panel. It's 2.8 degrees warmer at the end of the century there. The black curve with the grey shaded area around it is what the model comes back with as its optimum result, with the tipping point, the prospect of tipping points included, calibrated as I just showed you. And in essence, it comes back saying, hold on a minute, we can't let the world go to 3 degrees of warming. We should be doing everything in our power to limit warming. And that's expressed up in the top right, where the emission control rate in the original model in green was not 0, it was already something, and it ramped up over the century. But in black, once the social planner knows about the tipping points, they shut down half of fossil fuel burning immediately, and they shut it down completely by 2050. And to do that, they set the price on carbon emissions in the top left, the social cost of carbon, around 10 times higher than in the original model, at well over $100 per tonne of CO2 at present, and that ramps up over time. And that's what shuts down, that's, if you like, what shuts down emissions, and it's what limits the warming to less than 1.5 degrees in this model. We'll come back to that, because we're going to come back to what it would take to achieve that kind of objective. But in the meantime, I know that Robert at least wanted to talk to you about the latest work on the human climate niche. So a little bit of a change of gear here. But if you weren't convinced that climate tipping points were a good reason to be acting decisively on climate change now, this might convince you. So together with my good friend Martin Scheffer, colleagues Tim Kohler, an archaeologist, Jens Christian Svenning, who's got some expertise in demography, and Shushi, who's a fantastic data scientist, we thought about the question, what is the climate niche of humans as a species? So basically, pretty much any animal, or indeed any organism on the planet, has a preferred climate they like to live under. Obviously, humans like to live, or can live, in all sorts of places, from the Sahara to northwest Greenland, but the population density for sure isn't the same everywhere, and there is a peak or peaks, presumably at some level of temperature and precipitation. That's what we set out to identify. So the x-axis here is mean annual precipitation, the y-axis is mean annual temperature, and these are heat maps, and in the top row you've got the distribution of humans today, population density. You've got them 500 years ago, and you've got them 6,000 years ago from the best archaeological database that's just become available. And then where are crops, livestock, and GDP concentrated? And on the bottom row, you see that the available locations, the point density it's called, it looks very different to where we actually live. Actually, where we grow stuff turns out not to be that as well correlated with where soil fertility is highest or where net primary production is highest. But for sure, crops, livestock, and GDP seem to follow where the people are, and there appears to be preferred conditions. In particular, a maximum of human population density looks to be around 10, 15, 13, 14 degrees centigrade, and at moderate levels of precipitation. So if we just collapse the collapse onto the temperature or the precipitation axes for human population density, crop production, livestock, or GDP, it leaps out that in temperature terms, there's a peak of human population density, food production, and economic activity, and that peak centered on about 13 degrees centigrade. There is also, perhaps less clearly, but some kind of peak at what we might call loosely moderate levels of precipitation, and it definitely drops off under dry conditions, and it drops off less steeply under wetter conditions. The temperature niche falls out perhaps the cleanest, and I plot it again on the left here, where we're looking at the temperature niche at various times in the past, including 2 different data sets for 6,000 years ago, 500 years ago, 300 years ago. The present is in blue. Our attempt to fit the niche is the blue dashed line. And then the shocking result is the red line, which is under a 3-degree warmer world in 2070, which is under a thing called RCP 8.5 emission scenario, if you're curious. And with the what's called the SSP3 population projection, which we'll come back to, where people are projected to be in temperature space in 2070 is the red line on the left, with a bit of shading uncertainty around it. And my word, that looks rather different to where we've been living and building all our civilizations, etc., up to now, including this alarming result that the bigger peak is now at very high temperatures that hardly anybody experiences today, as we'll see in a minute. So, in case I forget to say why, there are two things going on here. There's the land warms faster than the ocean, so on average the land warms more than 3 degrees, but population growth is overwhelmingly projected to happen in already hot places, and that's skewing the distribution right. So we can play some games with this. We can plot how the apparent niche that we've just identified, the blue dotted line, where that is in geographical space. This is just the temperature niche for these plots, 6,000 years ago at the top, present in the middle, and then 2070, 3-degree warmer world at the bottom. You have to stare a little bit to start to see the large movements of the optimum niche in dark red. But you look at them, for example, in North America, how that optimum niche location moves quite a bit in latitude. We'll see this in more detail in a minute, but the crucial thing isn't what's happening where we live or in North America, but some locations in the tropics. So what I've done in this plot is I'm showing a background graph or map of mean annual temperature today, with on top of it some black areas, which are places that have more than 29 degrees C mean annual temperature today, and they're restricted to the edge of the Gulf and a few spots in the Sahara. And then in grey shading is areas projected to have mean annual temperature over 29 degrees C in this 3 degrees C warmer world. And the bad news is those grey shaded areas cover a large part of the Indian subcontinent, where more than a billion people live. They cover parts of West Africa, where we'll see in a minute there's huge projected population growth and already massive populations. And they cover much of Brazil, for example. This map shows you how the combined temperature precipitation niche is shifting, and places that are getting better is green and places that are getting worse are red, and dark red is really bad news, where it's getting really markedly worse. And again, same thing jumps out. Places like Nigeria, India, quite a lot of China, southern US, large numbers of people live in these places today. And on top of that, if you know anything about population growth that I haven't already muttered about in the talk, this is a beautiful reweighting of the world map by relative population density for 2018. This is what it's projected to look like in 2100. The great big balloon that blows up is Africa. That's where around 3 billion of the extra 3.5 billion people are projected to be at the end of the century, with 960 million projected to be in Nigeria alone. Well, that's alarming when you intersect that with the climate niche work. And I'm just showing you these things in a different way here. I'm showing you in the bottom plot the projected population distribution actually now in 2070 under one of these future scenarios. And if you know where Nigeria is, you can see that in a fairly dark brown. But recall that that was also a place projected to be experiencing these unprecedented high temperatures. And look at India as well, with further large growth in population and also projected to be experiencing unprecedented temperatures. So the question then obviously arises, would people just stay put? Would they be able to tolerably stay put when they're exposed to climate conditions that are out of the realm largely of experience and are apparently not conditions that have fared well for us at present or for thousands of years of our history? Or might instead people choose to move to stay in a better climate if they have the means to move? Well, we just did the calculations of the number of people that are essentially falling outside of the niche as we defined it under different warming scenarios. So 2.6 is the low warming, trying to limit warming to 2 degrees world. 8.5 is the high warming world, 4.5 somewhere in the middle. On the x-axis is ZG, zero population growth. All the SSPs, they're just different population scenarios. We can look at this in another way, and that's per degree of warming. Whichever way you cut the cake, you get back the result that about 1 billion people are going to be displaced from this apparent human climate niche for each degree of warming above present, in fact. Now, that should be enough information to hopefully convince you that we don't want to go there. Well, certainly we don't want to go to 3 degrees of warming if we can avoid it. Just to lighten the mood for a second, I'll tell you a tiny bit about some work we're doing on the side, which is to go back in time and ask the question, well, where did human civilizations arise on this climate niche? This is work in progress. But in simple terms, overwhelmingly on the dry side of the climate niche is the answer, which begs all sorts of interesting questions or inquiry about whether actually challenging conditions environmentally are the trigger for the rise of social complexity, because you need to be well organized and develop an elaborate water management system if you're to have any hope of continuing to stay or flourish under the dry side of the niche. And that certainly was strongly linked with the rise of those kind of technologies were strongly linked with the rise of early civilizations. Equally, we're doing some work on where or why might civilizations have fell in the past. Hard not to start thinking about that, given what I've said. And in particular, we've been curious about, could there be early warning signals for a tipping point, not just in the climate, but for the past loss of or collapse of civilizations? It's very hard to get good enough data to answer that question, but one case study work in progress where there is good data is for Pueblo societies in kind of southwest North America. We're talking about parts of southern Arizona, New Mexico, Mexico itself. Essentially, there's good enough data from the tree cutting ages of the trees that have been used in the buildings of the different phases of the Pueblo societies that you can begin to analyze time series data that show phases of growth and then collapse, repeated phases of growth and collapse of these civilizations, maize-based agricultural production. And a simple result at the moment that looks robust from our checks is that each of 4 phases of collapse of these ancient societies did carry early warning signals consistent with that collapse having some kind of tipping point positive feedback dynamics associated with it. But the latest on this analysis is it's not clearly collapse linked to climate change. So we can come back to that in the discussion about all the complex factors that could be intertwined in the collapse of a complex system taking the form of a civilization. Right, that was a lot of bad news. Let's change gear and then try to talk about some good news or some good uses of this complex systems thinking, because I've convinced myself this is where I need to be working as well. What positive tipping points can we find to try and avoid the bad climate-related tipping points? Because basically we've got a Herculean task ahead of us between now and 2050. So in a generation, we've got to go from a trend of rising greenhouse gas emissions, especially CO2, to net zero greenhouse gas emissions globally within 30 years. As a nation, the UK is committed to that and bound it into law. Look forward to everybody else hopefully joining us in that commitment. Whichever way you want to look at it, that requires transformative rates of change, and it's going to need non-linear dynamical change in society and our relationship with technologies and so forth. So this is where tipping points in different kinds of systems might come to our rescue. My argument is essentially we need to find, and those who have the power to do so need to encourage the triggering of some, what I'm going to glibly call positive tipping points towards this zero greenhouse gas emission future. And I'm obviously not the only person starting to sing from this hymn sheet. There's been some nice recent papers starting to scope out why on earth might we think there could be tipping point dynamics in the social realm, and what bits of the social realm. I'll give a few examples. I think hopefully we can all agree that we've seen tipping point dynamics before the present lockdown in terms of public awareness and stated feelings on the climate issue. So what's already known, and there are models for this in the literature, is that political revolutions have tipping point dynamics. They begin when one person changes their publicly stated preference to oppose the norms of their culture, if you like. And Greta kind of represents that person for the climate movement in recent years. She made a statement: "I'm not going to go to school unless you take this defining issue for my life and my generation seriously." And for each person that changes their publicly stated preference, it becomes incrementally easier for the next person to join them. And that's the basis of a positive feedback cycle in political revolution that others have modelled. And it's certainly what started to unfold with Greta. A few people joined her, and then before we knew it, we had tens and hundreds of thousands of people changing their publicly stated preference and telling their governments that we're in a climate emergency and we want to see you declare that as well and do something about it. So the last image there is the European Parliament voting to declare a climate emergency. Actually happened the day after last November I published that tipping points paper. So that was, and a few of the media outlets suggested there was a link, which I'm flattered by. But anyway, there's no point declaring a climate emergency unless you actually act on that. And that's the thing we're all still waiting for at some scale, is to see not just, I think there is an emergency from our politicians, but actually this is what we're doing to change behaviour and change the way we live to address that emergency. And this was a nice study by Scott Barrett and Astrid Dannenberg in the field of game theory that looked at the fact that tipping collective action to tackle climate change had its own tipping point dynamics. And basically they argued that the crucial control variable here, the x-axis, is our uncertainty about a bad climate outcome, a climate tipping point, let's call it that, where in the game you lose 90% of your remaining capital or asset. But what will happen persistently in these games, in the theory and in experimental tests, is if the uncertainty around a really bad outcome is too high, people fail to coordinate, or nations fail to coordinate to tackle the underlying problem. And we have what's loosely called a prisoner's dilemma or a tragedy of the commons. However, the dynamics tip below us if the uncertainty can be wrestled down enough. It was both by theory and experiment shown that you could tip the social dynamics to everyone clubbing together in a so-called coordination game to get serious and tackle the underlying problem. Well, let's hope, if there is such a tipping point, let's hope we can get ourselves to it, or that we're near it, because we certainly need it. I want to finish, though, by talking about tipping points in our relationship with technologies. First off, if you don't know it already, it's good to know that there have been profound tipping points in our relationship with technology in the past. This is an example of personal mobility. This is Easter Parade, 5th Avenue, New York City, as it says, in 1900. Everyone's in a horse-drawn carriage except one person in an automobile. 13 years later, the same Easter Parade, everybody's in an automobile, one person is left in a horse-drawn carriage. That transition in personal mobility within about a decade happened in a whole range of US cities. Now we might look back on it with some regret from a fossil fuel point of view, but what we should be doing is looking ahead and thinking, oh, what would it take for there to be rapid tipping points like that in our transport, energy and other systems. So I've been looking at some data for the uptake of electric vehicles with a friend and colleague called Simon Sharp, who's in the UK Cabinet Office and is part of the team putting together the next Conference of the Parties, number 26, on the United Nations Framework Convention on Climate Change. And Simon and I have spotted that, and we should all probably know, that there's been a tipping point in electric vehicle uptake in one country, Norway. The latest figures would put it as more than 50% market share. So EVs are out competing petrol and diesel vehicles. And that's because, in this case, of a policy intervention, the Norwegian government has some cleverly designed policy incentives that have put electric vehicles on price parity for the consumer with conventional fossil fuel vehicles, and that's tipped the dynamics. And once those dynamics have tipped, what was a minority technology can grow in scale, and there'll always be economies of scale as it increases. It'll make the EVs cheaper and cheaper over time. And eventually the projections are they should be cheaper than fossil fuel powered cars for obvious reasons, that they need much less maintenance, far fewer moving parts and so on. So that's one example of a tipping point in one nation. And if nations or jurisdictions, I should say, came together, they could take this tipping up point to a higher spatial scale. And that is if China, Europe and California all realise their mutual interest in triggering a tipping point to electric vehicles, because it would help them meet their stated climate goals. And in the case of China, it's the only hope they have of outcompeting Germany in car manufacture. Then they could certainly scale this thing up. One more example is to go into electricity production. This is a bit of background, just kind of fun, showing how energy capture into the biosphere changed over Earth history and into human societies changed over recent history. Of course, power generation is still dominated by fossil fuels, more than 80%, unfortunately. But there's some really encouraging trends that solar in particular, and also wind power, are cheaper, new for new as it were, than fossil fuels already in several nations. And solar in particular is projected to become cheaper than fossil fuels ever could be in the future. So we already see in some nations like China that it's cheaper now if you're building a new power station to make it renewables rather than coal powered. And within 10 years, it's projected that it'll make economic sense to close an existing fossil fuel powered station, a coal burning one, and replace, even though it's got useful life in it, and replace it with solar PV or wind power. And in the UK, we got one thing we might be able to be proud of amidst the misery of Brexit and everything else, and that is we've already, thanks to policy intervention, shut coal burning out of UK electricity generation. And that's no small feat, because coal used to be the mainstay of the backstop energy power supply for electricity in the UK. But through a mixture of the EU underlying carbon price in grey and the UK's own additional price on carbon, CPS it's called there, in blue, policy was able to create a situation where the price of switching from coal to gas for electricity generation was such that it basically made gas the obvious choice. And that put the nail in the coffin, as it were, of coal power and UK electricity generation, which has dropped precipitously since about 2013 to zero as of about last week. And in the meantime, the slack's been taken up by a massive expansion of renewable energy, and that the particular tipping point for coal in the UK is irreversible, because things like this have happened. This is the demolition of a coal-powered electricity generating power station at Didcot in Oxfordshire. That's the demolition of the cooling towers last year. Once you've gone to doing that, there's no going back. So yeah, sorry I took maybe closer to an hour than the 45 minutes promised, but my summary is that some climate tipping points might already have been passed, and certainly if we carry on the way we're going, they're going to become high impact, high probability events. Our existing knowledge of climate tipping points should already be compelling us to act decisively to limit global warming to well below 2 degrees C. And that means we should all our nations should be pricing carbon pollution at a pretty high level, way higher than most of them are. If that didn't persuade you, I've tried to show you that there's evidence we have, as a species, a preferred climate niche, and that niche is moving across spatially dramatically this century, and for each degree of additional warming, about 1 billion people will be falling outside of that niche and might well be tempted to migrate, and we can all join the mental dots as to whether that will be a tolerable transition in our nations. So yeah, my closing thought is really, we've got to change the narrative. If we're committed complex systems thinkers, we've got to spend some of our time and energy identifying ways of using that kind of thinking, our understanding of tipping points, to find the tipping points we're going to need to avoid the worst. I'll leave it there and try my best to jump out of screen share in Teams and switch my camera on and everything else. Thank you very much.
Okay, thank you very much.